are going to explain about the project titled VGGIN Net Deep Transfer Network for Imbalanced Breast Cancer Dataset. Introduction. Cancer, particularly breast cancer, is a significant health concern worldwide. Detecting it early can significantly improve patient outcomes. However, the diagnosis process can be complex and time-consuming for healthcare professionals. Deep learning, a subset of artificial intelligence, has shown exceptional promise in various fields, including healthcare. Convolutional neural networks (CNN) are a specific type of deep learning architecture well suited for image-related tasks. They can automatically learn patterns and features from images, making them ideal for medical image analysis and diagnosis. Transfer learning involves using knowledge gained from solving one problem and applying it to a different but related problem. In this case, the deep learning architecture leverages pre-trained layers from established models like VGG16 and Inception. By using these pre-trained layers, the network can benefit from their learned features, which can improve performance, especially when dealing with limited data or addressing class imbalance issues, where some classes have significantly fewer examples than others. Regularization techniques are used to prevent overfitting, a situation where a model learns to perform well on training data but fails to generalize to new unseen data. Data augmentation involves artificially expanding the training dataset by applying transformations like rotations, flips, or resizing to the existing images. Dropout is a technique that randomly ignores a fraction of neurons during training, which helps prevent the network from relying too heavily on certain neurons or features. The proposed network architecture is put to test using images captured at different magnification levels. This is important in medical imaging as different magnifications can reveal different details. The results of testing show improved classification performance compared to existing approaches, indicating that the proposed method can more accurately diagnose or classify images related to breast cancer, which is a significant advancement in the field. Objective. The primary goal of this project is to design a deep neural network architecture specifically tailored for classifying breast cancer dataset. An emphasis is placed on addressing the class imbalance problem, where certain classes within the dataset have significantly fewer samples than others, potentially leading to biased model predictions. The project aims to benefit from transfer learning by incorporating pre-trained layers from established models like VGG16 and Inception. These models initially trained on a large and diverse dataset called ImageNet, and by utilizing the pre-trained layers, the VGGIN net architecture can leverage the knowledge learned from ImageNet to improve its performance on the smaller imbalanced breast cancer dataset. To enhance the performance of VGGIN net, regularization techniques such as data augmentation and dropout are implemented. Data augmentation involves creating variations of existing data to augment the training dataset artificially, while dropout helps prevent overfitting by randomly deactivating neurons during training. The overarching aim is to achieve superior accuracies in breast cancer classification compared to existing state-of-the-art approaches. This implies a focus on not just developing a functional model, but one that outperforms current benchmarks in accuracy, which is crucial for practical deployment in healthcare settings. Beyond achieving high accuracy on a specific dataset, the project aims to validate the transfer learning concept of the VGGIN net architecture on other breast cancer datasets. By demonstrating its efficacy on different datasets, it showcases the potential of the architecture for broader transfer learning applications in the field of breast cancer classification. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages in the chosen programming environment. Common packages for deep learning projects include TensorFlow, Keras, NumPy, Pandas, and Matplotlib, among others. These libraries provide tools for data manipulation, model building, and visualization. Exploring the dataset. Breast cancer detection. This phase involves understanding the dataset for breast cancer detection. Exploratory data analysis (EDA) techniques are used to gain insights into the dataset structure, such as the number of samples, classes, distribution of classes, which reveal class imbalance and characteristics of the images. Image processing using image data generator. This is a powerful tool in deep learning for image augmentation. It generates augmented images in real time during model training, enabling the model to train on a more diverse set of data without actually increasing the size of the dataset in the memory. Rescaling the image. Normalizing or rescaling the pixel values of the images to a standard range, usually between 0 and 1, to ensure uniformity and faster convergence during model training. Shear transformation, zooming the image, horizontal flip. These are examples of image augmentation techniques applied using the image data generator. Shear transformation changes the shape of the image by shifting one part of the image over another. Zooming alters the scale of the image, and horizontal flip mirrors the image horizontally. These augmentations help increase the diversity of the training dataset and improve the model's ability to generalize. Reshaping the image. Ensuring that all images in the dataset have the same dimensions, resizing or reshaping to fit the input requirements of the neural network architecture being used. Building the model. Model building includes defining the layers, specifying activation functions, configuring loss functions, selecting optimization algorithms, and determining evaluation metrics. Training the model. This stage involves feeding the prepared and pre-processed dataset into the designed neural network model, such as VGGIN for training. The model learns to recognize patterns and features in the images through iterative optimization of its parameters using training data. Training involves forward and backward passes, forward propagation and back propagation to adjust the model's weights based on the predicted output and the actual target label. Flask framework with SQLite for sign-up and sign-in. Flask is a web framework in Python used for developing web applications. SQLite is a lightweight database commonly integrated with Flask for managing user-related information such as sign-up, user registration, and sign-in user login functionalities. This module likely involves creating routes and views for user authentication, registration, and login within the web application. User upload an image for analysis. This phase allows users to upload their images through the web interface. The uploaded image is then sent to the backend for analysis or processing. The given input is pre-processed. Upon receiving the user-uploaded image, this step involves pre-processing the image to ensure it matches the format expected by the trained model. This includes resizing, normalization, or any other required transformation to prepare the image for input into the neural network. The trained model is used for predicting the result. Once the input image is pre-processed, the trained neural network model, previously trained on breast cancer images, is employed to predict or analyze the uploaded image. The model uses its learned features and patterns to classify or detect features related to breast cancer in the input image. Final outcome is displayed through front end. Finally, the result of prediction generated by the model is displayed to the user through the web application's front end. This includes displaying the predicted classification of the uploaded image, whether it contains indications of breast cancer or not, providing relevant information about the analysis outcome. Algorithms used to implement this project, we have utilized the following algorithms. The first one is VGG16. VGG16 is a deep convolutional neural network architecture known for its simplicity and effectiveness. It consists of 16 layers, mainly using 3x3 convolutional layers and max pooling layers, culminating in 3 fully connected layers at the end. VGG16 was originally designed for the ImageNet Large-Scale Visual Recognition Challenge and has been widely used as a base architecture for transfer learning due to its straightforward structure and good performance. VGGNet. This architecture, known for its straightforward design, employs a consistent configuration of convolutional layers throughout the network, using 3x3 filters and interleaving them with max pooling layers to progressively reduce spatial dimensions while extracting hierarchical features. ResNet 50. ResNet 50 is part of the ResNet residual network family, known for its deep structure and the introduction of residual connections. These connections enable the passing of information from one layer to several layers deeper, mitigating the vanishing gradient problem and allowing the training of very deep networks. ResNet 50 specifically has 50 layers and has shown impressive performance in various image recognition tasks. GoogleNet. GoogleNet, also known as the Inception architecture, was designed by Google and is characterized by its Inception modules. These modules use multiple convolutional layers with different kernel sizes in parallel and concatenate their outputs to create a diverse set of features at each stage of the network. This architecture aims to capture both local and global information efficiently. GoogleNet won the ImageNet Large-Scale Visual Recognition Challenge in 2014 due to its accuracy and computational efficiency. As an extension, we applied other deep learning models to produce a more robust and accurate final prediction. Comparison graphs. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on register button here. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created. So I'm entering the username and the password and then click on sign in. We have logged in successfully. So here we need to upload the image, and after uploading the image we will predict the breast cancer. So click on choose file. I'm selecting the first image. Click on open. Now click on upload button. So here this is the uploaded image and the prediction is the patient is diagnosed with breast malignant. Breast malignant is cancerous growth or tumor in the breast with potential to spread. Now we will upload one more image and check whether the patient is having breast cancer or not. So click on try again. Click on choose file. So here I'm uploading the third image. Now click on open. Click on upload button. So here this is the uploaded image and it is predicted as the patient is diagnosed with breast benign. Breast benign, non-cancerous growth or condition in the breast. It means that the patient is not having breast cancer. In this way, by uploading the image, we can predict whether the patient is having breast cancer or not. Now click on logout. The conclusion of the project is the VGGIN architecture is specifically designed to tackle the challenge of classifying breast cancer. It does so by leveraging transfer learning, a technique where knowledge gained from solving one problem to improve performance, especially in scenarios with limited data. Moreover, it addresses class imbalance in datasets, a common issue where some classes have significantly fewer samples than others. This imbalance can skew the model's learning, leading to biased predictions. The architecture combines transfer learning techniques utilizing pre-trained layers from VGG16 and Inception to leverage the learned features from ImageNet. By doing so, it enriches the breast cancer classification task with valuable knowledge learned from a diverse range of images. To further enhance performance and prevent overfitting, data augmentation techniques are used. This involves creation variations of existing data by applying transformations like rotations, flips, or resizing. Additionally, dropout is employed, randomly deactivating neurons during training to improve the model's generalization. Fine-tuning involves adjusting the pre-trained layers of VGG16 and Inception specifically for the breast cancer dataset. By fine-tuning, the architecture adapts its learned representation to better suit the characteristic of the breast cancer images. This adaptation results in significant performance improvements, leading to more accurate classification or detection of breast cancer-related features. The success of VGGIN net on the breast cancer dataset indicates its potential for broader applications beyond the original dataset. This showcases the architecture's versatility and adaptability, suggesting that the knowledge and features learned from transfer learning can be effectively applied to different datasets or tasks related to medical imaging and potentially other domains.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.